Hello. Now we want to discuss a little bit what we did. So we started from studying a transistor. We found that with one transistor we can implement an amplifier. Then we made something a little bit better, which was a differential amplifier, and in order to do this we needed to discover the current mirror circuit. Then with that we have built an operational amplifier, which is something that is very close to an ideal amplifier, but not yet, because the gain of it is very high, too high maybe, or let's say it's only that value that the manufacturer gives us. And then we found that by using that operational amplifier we can assemble another circuit like this one, the non-inverting operational amplifier, which gives us the freedom of choosing the value G, the gain of this system, so the ratio between the output and the input. And we also noticed by doing some calculation that because of this property that the gain is open loop gain A is very high, then this gain does not depend on the characteristics on the amplifier, but it depends only on the characteristics of what is called the feedback network, which is made of those two resistors. So this operational amplifier configuration is called non-inverting because if we carefully study the sign of a signal applied to the input and the sign of the signal applied to the output, they have the same sign. So if we apply a sinusoidal input, we have a similar sinusoidal output with the same phase, but with a bigger or smaller amplitude, depending on the feedback network. So because this is a non-inverting amplifier and the gain of it is defined by this equation that we found, we have to notice that it's not possible to have a non-inverting amplifier with a gain which is less than 1, because it's 1 plus something, which is a ratio of two things, two resistances which are both positive, and so 1 plus something positive is always bigger than 1. But this is not a problem for us, because in case we want to have a smaller output, we can again put a voltage divider here, for instance, at the end of it, and consider this as a output, and we know how to reduce a voltage. Reducing a voltage is simple, it's amplifying and it is difficult. But now we want to do another thing. We want to consider the fact that we made use of a two input, so a differential amplifier, but in the end it came out that this equivalent amplifier has only one input, this one, because the second one has been used for setting the gain with the feedback network. So we are interested now in having a full differential amplifier, and so we have to go for this circuit. So we don't calculate all the formulas for this circuit because it takes quite a long time. We just discuss it. So we can notice that this is a sort of non-inverting amplifier, and also we have another non-inverting amplifier here. And then there is another thing here, which is a sort, actually is a differential amplifier. So with this configuration we have one good thing. We have that the entire circuit is a differential amplifier respect to those two inputs. Those two inputs are very sensitive because they are directly attached here. There are no resistors or whatever, so they both have a very high input impedance. Remember, there is a MOSFET at the beginning of those circuits here, the gate of a MOSFET. Then we can set the gain, we don't do this now, by choosing appropriately all those resistors. The gain will not depend on the gain of the individual amplifiers, which is very high for all three of them, and the output is differential. So this configuration is called a 3-op amp configuration, or also instrumentation amplifier, and this is the one which is the core of every neural amplifier for neurophysiology. So what is interesting for us is to understand how it works from the point of view of the functional behavior. So let's say that we have such kind of an amplifier with a certain gain G, and we attach two things to the inputs. So at one input we put an electrode very close to a neuron, for instance. At the other input we attach another type of electrode made in a way, and we will see how in the end of this course, which is able to collect signals from many neurons, so a sort of average value of a population of neurons. But there is some noise. So if we make those two terminals here physically very close each other, like imagine you have two wires like a probe that goes in a place, and those two paths are close each other, it's very likely that if there is some noise in the environment, they will pick up the same amount of noise. So if there is noise, the noise is kind of the same in both inputs. But this is a differential amplifier, so it will take the difference of this, and therefore this noise is cancelled, and what you get is just that the output is a coefficient, your gain, let's say 1000 for instance, which is a popular value in order to be able to amplify an extracellular voltage signal. So G multiplied the value of your neuron minus the average of a population of neurons, which is called local field potential. Local field potential. So if you know that the signal of a neuron is a sort of spike like this, then this thing here will produce as an output, assuming that the neuron is spiking, a series of spikes overlapped with a voltage which is the average of the others, and this happens because of a specific type of electrode we used here, which is different than this one. So this electrode is called the signal electrode, signal, and this other one is called the reference. frequency. And they are not manufactured in the same way. So if you do this, then you will have that the output signal is something like this. So V output is something like this. It's a spike, another spike, another spike, another spike, another spike, another spike, something like this. So usually the local field potential is much bigger in amplitude but much slower in frequency. And then we take advantage of what we studied about the filters. So for a signal like this, I switch to the blackboard. So if you have a signal like this out of this amplifier, whatever, let's say something like this. If you put this signal into a filter, which is a high pass filter, so we take this and we put it here, then this signal, this filter will produce an output which is the original signal, but we remove the low frequency components because it's a high pass filter. So we can tune the values of the high pass filter in order to remove this very slow signal, and then the result is just the spike train. So not all the times what is high frequency is noise. In this case, the high frequency represents the signal of interest. But you might be interested in recording the local field potential. So in this case, you take the same signal and you apply a low pass filter to it in order to be able to cut off all the high fast oscillation, and you keep only this. So with filters you can separate different parts of the signals and you can analyze them later. So this is why it's important to have such kind of filters. So sometimes during the recordings you have one frequency component which is quite nasty, is 50 Hertz, or in US maybe it's 60 Hertz, and it comes from the power outlets. So we are fully surrounded by 50 Hertz noise because everything that we power, something like a computer, whatever, takes power from 220 volts at 50 Hertz in Europe. So it is highly possible that you have a 50 Hertz noise present in your signal. So you can remove that frequency component by applying a notch filter tuned around that 50 Hertz. Or whatever frequency you want. Okay. So this is why we want to have such kind of amplifiers. Okay, so next time we will put this aside for a moment and we will speak about a different way of using amplifiers, because this is a so-called analog amplifiers. It takes a continuous variable at the input, which is the difference, the differential signal here between V1 and V2, whatever it is, and it amplifies it by a factor in a continuous way. But this amplifier has a range of voltage, because we have to remember that all of those amplifiers here are powered up by a battery, which we call VCC and minus VCC. And therefore the output can never exceed this range, plus and minus VCC. So minus VCC is smaller than V out, which is smaller than plus VCC. So what happens if I put an input here, or for instance, for simplicity, here, if you prefer, we have just one input. What happens if I put an input of, for instance, 5 volts, and the VCC is 5 volts, minus VCC is 5 volts, and the gain is 100. So I don't have 500 volts at the output. I don't have this. I have the maximum of what this guy can give, which is 5 volts. So in this condition we say that the input is saturated, or the amplifier is saturated, and then it becomes useless from the point of view of the amplification of analog signal. So the situation would be something like this. Let's say we have a signal at the input, and the output is like this, and then it's clipped. Sorry, I wanted to do with the same frequency in order to be compared. So let's say that this is the input, and the output is like this. So the signal maybe would like to be like this, but it can't, because this will surpass the plus VCC and minus VCC. So if you amplify a signal, like a sinusoidal signal, by a very big factor, this part becomes very steep, and at a certain point you have a flat plateau. So the signal tends to be more square like this in the end. So next time we will see that we can take advantage of this condition in order to work with amplifiers that will amplify only 2 values. Let's call it 1 and 0. And therefore, with this, even if it is not useful in order to amplify analog signals, it is useful in order to create operations with signals, mathematical operations with signals, in a new form of calculus, which is called Boolean algebra. So we are speaking of digital circuits, 1 and zeros. Okay. So next time we will speak about those things, digital circuits.